In the previous lessons of this section, we have explored how computers use binary to represent numbers. We've seen how IP addresses and subnets work at the binary level. But computers don't just work with numbers, they also need to store and transmit text. So that's what we're going to talk about in this lesson. The character encoding systems of ASCII and Unicode. Understanding these systems is surprisingly important for cybersecurity. Text encoding issues are at the heart of many security vulnerabilities, from SQL injection attacks to malware obfuscation techniques. So I'm hoping that by the end of this lesson, you'll understand how text becomes binary and you'll recognize why does this matter for your security work. We'll start with trying to understand the challenge that early computer scientists were up against. They needed a way to represent letters, numbers, punctuation marks, and other characters using only binary data. In concept, it may have been straightforward. Assign each character a unique number. Store that number in binary. The letter A could be assigned 65, B 66, and so on, perhaps. But an immediate problem arose with this idea. If different computer manufacturers used different numbering schemes, computers would not be able to communicate with each other. If one system said that 65 was A and another said that A was 193, the text would be garbled when transferred between them. So obviously the industry needed a standard, a universal agreement on which numbers represented which characters. That's where ASCII came in. ASCII stands for the American Standard Code for Information Interchange, and it was developed in the early 1960s and became the dominant character encoding standard for decades. ASCII uses 7 bits to represent each character. With 7 bits, you can represent 2 to the 7th power, or 128 different values. So that's enough for all the uppercase letters, all the lowercase letters, the digits 0 through 9, common punctuation marks, and a set of control characters. The uppercase letter A is assigned the decimal value of 65. In 7-bit binary, 65 is 1 with 5 zeros, and then finishing with the 1. So take a moment and verify that. Our place values for 7 bits are 64, 32, 16, 8, 4, 2, and 1. For 65, we need 64 plus 1, so we have a 1 in the 64 position, zeros in the middle positions, and a 1 in the 1 position, giving us that 1 with 6 zeros and a 1 at the end. The uppercase letter B is 66, which is 1000010. In binary. The uppercase letter Z is 90, which is 10, 110, 10 in binary. For lowercase letters, the pattern continues but with higher values. Lowercase a is 97, which is 1100001 in binary. Notice that 97 is exactly 32 more than 65. This 32 value offset between uppercase and lowercase letters is intentional and makes case conversion simple at the binary level. The digit characters also have ASCII values. The character 0, not the number 0, but the character that displays as 0 is ASCII 48, which is 0110000 in binary. The character 9 is ASCII 57. So why am I saying not the number but the character? Well, there's a difference between the number 5 and the character 5. The number 5 in binary is simply 101, but the character 5 that you see on screen is ASCII value 53, which is 110101. In binary. This distinction matters when you're analyzing data or writing code. Some key ASCII values worth memorizing. Uppercase A through Z is 65 through 90. Lowercase a through Z is 97 through 122. Digits 0 through 9 are 48 through 57. The space character is 32. The new line is 10. Carriage return is 13. Tab is 9 and a null character 0. The values 0 through 31 plus 127 are control characters. These don't display visible symbols but instead control how text is processed. The null character 0 marks the end of strings in many programming languages. The new line 10 creates a new line and the tab 9 creates horizontal spacing. Now you'll notice that we said ASCII technically requires only 7 bits, but computers are typically working with 8-bit bytes. So what's going on with that extra bit or that missing bit? Different systems used that 8th bit in different ways. They created what we call extended ASCII. By using all 8 bits, you could represent 256 characters instead of 128, adding room for accented letters, graphical symbols, or other characters. The problem was that there was no single extended ASCII standard. IBM created one version for their PCs. Apple created a different one for Macintosh. European countries created versions that included their specific accented characters. Now, this fragmentation caused endless compatibility problems. A file created on one system might display completely different characters when opened on another system. The character you intended as an accented E might appear as a completely different symbol on somebody else's computer. And this chaos really is why Unicode was eventually developed. Before we go further on that topic, though, let's talk a little bit more about why ASCII and character encoding matter for cybersecurity. There are several areas of cybersecurity work where it'll be helpful for you to understand ASCII. There's analyzing network protocols. Many network protocols, including HTTP, SMTP, and FTP, are text-based and use ASCII encoding. When you're examining packet captures or debugging network issues, you'll see ASCII data constantly. Being able to recognize ASCII values helps you understand what's happening in the traffic. Now let's think about examining malware and suspicious files. When analyzing a potentially malicious file, security analysts often look at the ASCII strings embedded in it. Commands, URLs, file paths, and error messages stored in malware can reveal what it's designed to do. Tools like the strings command extract readable ASCII data, text, from binary files. And understanding ASCII helps you interpret what you find. Understanding encoding-based attacks is another one. Attackers often use character encoding tricks to bypass security filters. A web application firewall might block requests containing the word script, but fail to block requests where script is encoded differently. And then when working with hexadecimal representations, in security tools and log files, you'll often see text displayed in hexadecimal. Each ASCII character's hex value appears instead of the character itself. For example, the hex value 41 represents uppercase A decimal 65, and 20 represents a space decimal 32. Being fluent in ASCII helps you read these representations quickly. There's also cryptography and hashing. When you hash a password or encrypt text, you're actually working with the binary representation of that text. The string password becomes a specific sequence of bytes based on its ASCII values. And that byte sequence is what gets processed by the cryptographic algorithm. For example, the word hi in ASCII, you've got H equals 72 equals 0100100 in binary equals 48 in hexadecimal. Lowercase I equals 105 equals 011010001 in binary equals 69 in hexadecimal. In a hex dump of network traffic or a file, hi would appear as 4869. Recognizing that 48 is uppercase H and 69 is lowercase I becomes second nature with practice. So ASCII worked well for English text, but it had fundamental limitation. 128 characters, or even the 256 characters with extended ASCII, isn't nearly enough to represent all the world's writing systems. Think about Chinese, which has tens of thousands of characters. Japanese uses multiple writing systems. Arabic and Hebrew are written right to left. Many languages have accented characters that ASCII never included. The world needed a universal character encoding system. So that's why they brought Unicode to the table. Unicode's aim was to provide a unique number called a code point for every character in every writing system, both ancient and modern. The current version of Unicode defines over 150,000 characters covering 161 scripts, including Egyptian hieroglyphics, musical notation, mathematical symbols, and even emoji. Each Unicode code point is written as U+, followed by a hexadecimal number. For example, you can see on the screen, plus 0041 is uppercase A, the same as ASCII 65. Plus 0048 is uppercase H. Plus 00E9 is the accented letter E. Plus 4E2D is the Chinese character for middle or center. U plus 1F600 is the grinning face emoji. The first 128 Unicode code points, U plus 0000 through U plus 007F, match ASCII, and this was intentional to maintain backward compatibility. But it gets more complex. Unicode defines what characters exist and assigns them code points, but it doesn't specify exactly how those code points should be stored in as bytes. That's the job of Unicode encoding formats, and there are several, numerous. So UTF-8, that's the dominant encoding standard. Over 98% of websites are using UTF-8 encoding. And that's UTF-8 is a variable length encoding, meaning different characters use different numbers of bytes. ASCII characters, the first 128 code points, just use 1 byte, which is identical to their ASCII representation. Characters from other languages might use 2, 3, or even 4 bytes. So for ASCII characters, U plus 4 zeros to U plus 007F. UTF-8 uses exactly 1 byte, and that byte is identical to ASCII, and the letter A is still 01000001, exactly as it was in ASCII. This means any ASCII text is automatically valid UTF-8 text. For characters U plus 0080 to U plus 07FF, UTF-8 uses 2 bytes. These include most accented Latin characters, Greek, Cyrillic, Hebrew, and Arabic. For characters U plus 0800 to U plus FFFF, UTF-8 uses 3 bytes. This range covers Chinese, Japanese, and Korean characters, among many others. For characters U plus 10,000 and above, UTF-8 uses 4 bytes, including emoji, historic scripts, and rare characters. The byte patterns in UTF-8 are designed so that a program can always tell whether it's looking at a single byte character, the start of a multi-byte character, or a continuation byte within a multi-byte character. This makes UTF-8 self-synchronizing, meaning if you jump into the middle of a UTF-8 stream, you can quickly find the start of the next character. Take a look at the bit patterns on the screen and see the 1 byte, 2 byte, 3 byte, 4 byte characters, how they start. The leading bits tell you how many bytes form the character. The X positions hold the actual code point data. While UTF-8 dominates the web, though, you'll encounter other Unicode encodings in cybersecurity work. UTF-16 uses 2 bytes for most common characters and 4 bytes for less common ones. It's used internally by Windows and Java. When you see text files from Windows systems, they might be UTF-16 encoded. UTF-32 uses exactly 4 bytes for every character, making it simpler but less space efficient. It's rarely used for storage or transmission, but sometimes appears in internal processing. Each encoding has different byte sequences for the same text, which matters when you're analyzing files or network traffic. A file that looks like garbage might simply be UTF-16 text, viewed as if it were UTF-8 and vice versa, or other ones. Unicode does introduce several security concerns that every cybersecurity professional should have some understanding of. Homograph attacks exploit the fact that many Unicode characters look identical or nearly identical to ASCII characters. The Cyrillic letter A, which is U plus 0430, looks exactly like the Latin letter A 0061, U plus 0061, but it has a different code point. An attacker could register a domain like apple.com using the Cyrillic A instead of the Latin A. To a human eye, it would look like apple.com, but it's actually a completely different domain. And this technique has been used in phishing attacks. Encoding-based filter bypass is another concern. A web application might filter out dangerous characters like angle brackets to prevent cross-site scripting. But if the application doesn't properly normalize Unicode input, an attacker might use alternative encodings or Unicode equivalents to slip past the filter. Overlong encodings were a significant vulnerability in early Unicode implementations. UTF-8 has rules about using the shortest possible encoding for each character. For example, the / should be encoded as the single byte 2F, but older systems might accept an overlong 2-byte encoding that represents a /. Attackers could use these overlong encodings to bypass security filters that looked for the standard single byte version. Null byte injection exploits how different systems handled the null character U plus 0000. In C-based programs, a null byte terminates a string, but other systems might process the full Unicode string. An attacker might submit a file name like malicious.exe $00.txt, where %00 is a null byte. A validation function might see it as a .txt file and allow it, while the file system truncates at the null and treats it as a malicious executable. Right to left override characters can make text appear different than it actually is. Unicode includes control characters that change text direction, which is necessary for languages like Arabic and Hebrew. But attackers can abuse these to disguise file extensions. A file named invoice open bracket RLO closed bracket fdp.exe would display as invoiceexe.pdf because the right to left override reverses the final characters, making a dangerous executable look like it's a PDF file. So understanding this character encoding is really essential for cybersecurity work. Input validation, output encoding, and security filtering have to all account for Unicode's complexity. If you're reviewing security logs, you might see text represented in different ways. A raw ASCII, hexadecimal bytes, URL encoding where a space becomes %20, or HTML entities. Understanding the underlying character encoding helps you decode and interpret what you're seeing. Malware authors often obfuscate strings to avoid detection. They might XOR the ASCII values with a key, use Unicode escapes, or employ other encoding tricks. Knowing how text is represented helps you reverse these obfuscations. When testing web applications, you'll try various encoding techniques to bypass input filters. Understanding UTF-8 structure, percent encoding, and HTML entities helps you to craft effective test cases. If you're performing digital forensics and examining a hard drive or memory dump, you need to recognize text in whatever encoding it's stored. Windows systems often use UTF-16, like we mentioned, while Linux systems typically use UTF-8. Knowing what to look for helps you recover relevant evidence a lot more quickly and effectively. So let's just do a quick summary. ASCII assigns numeric values to 128 characters using 7 bits per character. The uppercase letters span values 65 through 90, and lowercase letters span values 97 through 122. Digits span 48 through 57. ASCII remains important because it's the foundation of text encoding and appears constantly in security work. Extended ASCII used the 8th bit to add more characters, but the lack of standardization caused compatibility problems. Unicode provides a universal character set with over 150,000 characters, each assigned a unique code point. Unicode encodings like UTF-8, 16, and 32 specify how these code points are stored as bytes. UTF-8 is the dominant encoding on the internet just for websites. It's variable length, using 1 to 4 bytes per character. Its first 128 characters match with ASCII for backward compatibility. Unicode introduces security concerns including homograph attacks, encoding bypass techniques, overlong encodings, null byte injection, and right-to-left override attacks. Security professionals have to understand these issues to build and test secure systems. Throughout your cybersecurity career, you'll encounter character encoding and network analyses, malware investigation, web security, forensics, and countless other contexts. The foundation from this lesson should hopefully serve you well.